Okay, so first of all, welcome once again. Thanks for making the time, and thanks, Sebastian, for a wonderful presentation. What I'm going to do is to describe in the first part of my presentation some of the fundamental systems issues that we had to solve to get a scalable high-performance database. And then I will switch gears to talk a little bit about the latest AI-based developments and how the work that we have done um, naturally fits into that kind of environment. Okay, let's get started. So just to set the stage, I just want you to understand the kinds of applications that we designed Aerospike for. These are actual use cases from our deployment over the last, I guess, 13 to 14 years. Just to give you an idea, I'm not going to go into the details of each of this, but you can see that in every one of these areas, some of the top companies in the world actually uses us, uses this database, and everything that I'm going to talk about is going to essentially describe the way we went about building such a system that can have such a wide range of real-time applications. So the first thing about a modern database is to ensure that it can be elastic. So that's where kind of we started ourselves. And one of the most important things that we decided on early is to use a shared nothing database cluster. We are, going forward, we'll be adding more kind of configurations, but this is kind of where we started. And the primary or the most important aspect of a distributed system is to ensure that there are no hotspots. We were talking earlier with some of you about spikes in load. I mean, when we're talking about the kinds of use cases, I briefly flashed it before you. They're all about consumer-oriented use cases. There are a lot of people in the world who are using these services. And when they come in, they could come in terms of spikes. One of the things, I'm originally from India, and cricket is kind of really crazy in India. So we have a customer called Dream 11, which deals with fantasy cricket league. And every time before a cricket match or game starts, there is a huge spike in this. Right? That's just one aspect of things, right? And there's also there are use cases for Aerospike in a large brokerage firm. On a daily basis, they actually do more transactions than Google searches in the same day. So you can see the kind of scales that we're talking about. They're not really comparable in terms of what a Google search has to do versus what transactions have to do. But in terms of numbers and scale, that's what we're talking about. And you cannot afford to have any downtime. So not having hotspots is really important. There's a whole bunch of technology that goes into making this work. Essentially every node being identical is an important part of it. It's all written in C, so it makes sure that there are no garbage collection kind of hiccups like you hit with Java, for example. All of this is essentially designed to avoid hotspots. Dynamic cluster management, you can add nodes, on the fly. You can make sure that nodes can be removed. Of course, you have no control over removal because system in a distributed system can get disconnected. Portions of the system can get disconnected from the rest of the cluster. Nodes can go down. And all of those are expected. So all of that, I think we do. But there's one unique thing that Aerospike does is in the clustering protocol, we also include the client in order to optimize access. So every access from an application going through our client libraries to the database is a single hop. And this is fundamentally important because then you can actually scale this linearly over time. And there's also a whole bunch of work we did in managing transactions, which are basically the read-write access or for either a key value or a document or one of those individual records. But also there are long-running tasks that happen. Sometimes you scan the database in order to do things. Sometimes you run queries against it using secondary indexes. Other times, you need to defragment the disk as you are actually filling it up. I'll talk a little bit about that. Or, for example, batch deletes, and there's so many large, long-running transactions that have to happen, and real-time prioritization is important. once again, writing it in C, taking advantage of various optimizations, in terms of how you use the threading layer and so on, is really important to make that work. So fundamentally, no hotspots. The other kind of important pillar of our scale-out algorithm is the data partitioning architecture. Aerospike essentially clusters the data by itself. It is quite different than every other database you're used to. Probably the biggest similarity is with Cassandra in terms of they use linear hashing, but our partitioning scheme has certain advantages even compared to that. And the idea is when a node goes in or out of the cluster, you want to make sure that the remaining nodes have an equally balanced load. And that's kind of what this partition scheme does. So the way we do the partitioning is we take every key and we assign it to one of 4096 partitions. So that is the number of partitions. And we do that using an algorithm called the RIPE-MD 160 algorithm. It's not an Aerospike invented algorithm. It is a cryptographic hash algorithm, which is extremely robust against collisions. And it's truly randomizes it. So that's really important. So the digest which we create, the RIPE-MD 160, 160 stands for 160 bits, which is basically 20 bytes. The digest size is 20 bytes. And then we use that. We take about 12 of those bits to assign the partition ID. And then we map those partitions to nodes. The picture on the right here is showing essentially how you would map 4096 partitions to a 5-node cluster, N1 to N5 are the node numbers. And as you can see, each partition, right, you see P1, P2, and, okay, I can do this, P1, P2, and P3, they're all assigned to different masters. Master is basically the first copy of the partition. It is in some node. And then the second copy of the partition, a third copy, and fourth copy, and fifth copy. This is a 5-node cluster. So this table has essentially 5 columns and 4096 rows. The interesting thing that happens is when a node goes off. So let's say node, in this particular case, N5 is down. So you can look at partition P2, and N5 happens at the second replica, and then essentially N2, N4, and then it becomes N3 and N1. Now, this is not that interesting because, okay, actually you can make it interesting. If it's a 3-copy system, then the first 3 columns are to be used in the system, right? I mean, this is basically how this partition table works. If you run the cluster with 2 copies, the first 2 columns will be used. In this particular case, if you're running a 3-copy system, the third copy just went away. And the third copy has to be copied into N3 when the system is running without node 5. And this one, all of this happens automatically, okay? And the way this partition assignment happened, and that's essentially is to ensure that the original algorithm was minimizing the data movement when the partition map changes. Minimizing data movement means that essentially you will take the minimum number of copies of missing partitions to maintain the replication factor when a node is added or removed from the cluster. Over several years, we found that that created skew in terms of data. Remember the whole thing about not having hotspots? If you had actually a skew in terms of how your data is assigned, partitions are assigned to nodes, you could have more partitions to a node. So if your skew is about 20%, so you end up basically some nodes having 20% fewer partitions, some nodes 20% more partitions than the average. So you almost get like 30% of variation of load, assuming uniform distribution of data to keys, and that actually is guaranteed pretty much by the RIPE-MD 160 algorithm. So the end result is we actually had to improve that algorithm to trade it off, and that's what the partition balance algorithm essentially, we make some adjustments to the assignment of partitions to nodes, and the way we do that, we will actually increase some of the movement of data when nodes go in and out of the cluster. However, in the actual load will be uniformly balanced. So you pay more during rebalancing in order to have a properly distributed load in your cluster. Okay? So these are the kinds of trade-offs we have done. There's more, someone was asking me earlier, we have actually published research papers on, in conferences and so on this, and I can point you to those if you're interested. The rest, this basically slide says that we have written code with various subsystems which will implement some of the things I just talked about, ensuring no hotspots, ensuring dynamic cluster management, ensuring partition mapping like we talked about. So we have various systems like the heartbeat subsystem which detects when nodes go in and out of the cluster, as well as a clustering subsystem which will be able to reform a cluster if nodes are changed in the cluster. And then you have data which is moving back and forth, like we talked about, the assignment of the partition map. All of this actually happens quite well. Here's an example. When you add a node to a 3-node cluster, then you see that, let's say we have a 3-node cluster with 2 copies, okay? So each of those nodes will have 1/3 of the data, and then as master and 1/3 as replica. Together with 3 nodes, you have 2x the amount of data. You have 2 copies. Now, when a 4th node is added, 1/12 of the data from each of those nodes for master has to be copied to that new node, another 1/12 for the replica. So eventually you end up with 1/2 of the data, quarter of master and quarter replica partitions in all of the 4 nodes. All of this happens automatically, using these various pieces of code that we talked about. Okay. Now let's go to scaling up. So this is okay. Scale out itself is unique in Aerospike, but I wouldn't say it is too much further than what other people do, even though our algorithms obviously have stood the test of time in terms of generating availability for these use cases I talked about over a decade. We have systems which have been running for over 10 to 12 years with absolutely no downtime, for example. The hybrid memory architecture is one of the foundational aspects of Aerospike. What we have done is leveraging SSDs as well as DRAM to provide in-memory access at low latency. A typical database, typically let's take any database, doesn't matter, which is, it doesn't have to be only relational or NoSQL. It could be any other database other than Aerospike. Essentially, works as it's shown on the right side. What happens there is the data is essentially brought in to a page cache, and it's read off of that. And that's kind of how it works. It's a buffer pool-based strategy. You bring data from disk, you bring it in, and then you basically read it. That is not the approach that Aerospike takes, because Aerospike relies on SSD behavior. SSDs can allow you to do random access reads directly off the disk. So we don't actually bring the data to memory in a buffer pool and try to manage the buffer pool. We basically read directly off of disk. However, it comes with a catch. SSDs, you can't actually write in place. You will wear out the cells of the flash storage. So we actually built out an entire continuous non-disruptive defragmentation scheme on the backside using large block writes. So we have to write a file system which can directly read the data off the disk, but it has to do writes differently. And that's fundamentally how our hybrid memory architecture works. It keeps the index in memory. The index contains the digest I talked about earlier. So essentially, you have 64 bytes of index, which is, the 64 bytes is chosen for optimization reasons because it is the same as a cache line in most modern processors. And that means that it can be cached really well for repetitive operations. So it can be really, really fast in memory. And then we will be able to go directly to disk to read the data. So there's only one read for SSDs, and this can be done in sub-millisecond. And given that the SSDs have been continuing, this was actually designed in 2009. Okay, we have patents for most of the things I'm talking about here. About 15 patents granted, and more on the way. But the important thing is, what we can do with this is we've expanded the amount of data that can be accessed in real time on a particular node, because you can stick 10 to 20 to 30 terabytes of SSDs per node, while you're probably limited to about a terabyte maximum of DRAM in the largest instances. This means you have increased the amount of real-time data per node to be 10x, 20x, and so on. Let's just say 10x, which is a reasonably conservative number. What that means is the cluster sizes with Aerospike will be 10 times smaller at scale than every other database for real-time access. You'll still get multiple, millions of transactions per second on clusters, with every read and write being sub-millisecond. That's what allows this, and the cluster size will be 20 instead of 200 or more. And that's fundamentally a huge, huge advantage. Now, so I talked about putting a lot more data per node. which means, and if you have 20 nodes instead of 2,000 nodes, I'm sorry, 200 nodes, and you're running, let's say, 10 million transactions a second, you're going to do each of those 20 nodes, you're going to do 10x the transactions per second as you would do in the 200 nodes, because you're still running the same workload. How does that work? Because you've now increased the amount of data stored, which can potentially be accessed in real time by 10x. The transaction load is going to go 10x. In order to make that work, we spend a lot of time actually, working on CPU and network, optimizations. We looked at the multi-core. We have multiple cores. We can align cores to threads. We can align, sockets. We can do NUMA pinning. We also did ADQ, which is essentially a way to align network requests to threads on a CPU. So you can go all the way from the network. It's like a virtual circuit. When basically a bunch of interactions are happening from some source going through a network card to the CPU, to the thread, to the CPU, you can actually make it really, really fast. I mean, if you're on a freeway, analogy is if you're on a freeway, instead of having all the cars, go randomly on the freeway, you can actually figure out where the end point is and align each of those, like pretty much like a train, right? That's kind of what's happening here. All that means is we can, and look at the numbers here, right? With just simple NUMA CPU pinning, we're able to get about 8.6 million transactions a second. This is just purely in memory transactions, okay? We're just trying to show that we can do a lot more transactions per second memory. And then with the network-based, alignment, we could show 15.3. This happened together with Intel. But basically, what we are saying is we can actually do 10x the transactions per second easily if you put all the data together. So we can still deliver for you the same throughput you would get from a 1,000-node cluster in a cluster which is 100 nodes. Same amount of data, much better performance actually in many cases, but also very predictable performance, which actually Sebastian talked about. That's essentially the goal of all this, okay? So what do we do with this, right? I'll talk a little bit about some of the algorithms we've invented for distributed transaction capabilities, because fundamentally, Aerospike is a database. The goal is to keep the data safe, but also, and then the high performance is just a means to achieving some of the transactional goals of consistency, reliability, durability, and so on. The asset properties, if you wish. So I won't go too much into the details here, except to point out that we use a different consistency mechanism than what probably you have seen so far. We use it based on roster. Roster is nothing but a fancy name for the list of nodes in a cluster. Okay, and what we do with the roster is we follow certain rules in terms of availability. So all of this performance that we have enables us to do writes with a write all mechanism, which means we can write, every write to Aerospike will write every copy of the data item in Aerospike. We are talking about strong consistency here. Think of it as something which you can use for money transfer, operations. You can use it for healthcare apps. I mean, places where the data integrity is really important, and the immediacy of the data is also important. So when you make a change, be it some money is transferred from one account to another, or be it some new test has happened for a patient, and you're actually storing it somewhere. All of this would require you to be able to have access to the latest value of the data immediately after the write has happened, no matter which part of the cluster you're actually accessing. And that's fundamentally an important, that's only one half of what Aerospike can do, but that's an important part. Okay, it's strong consistency. Now, if you look at it, right, I'll just take you to this example a bit. When you have a roster of 5 nodes, and there is, let's say there are 2 copies, and I'm going to treat it as a partition by partition scheme, because I talked about how we partition the database into 1496 partitions. You can then treat each of those partitions as its own database. So it's a divide and conquer algorithm. So if you can solve for one partition, and then you can it basically solve for the whole thing, because you just do it 1496 times, right? There is one partition here which is a master in node 5 and a replica in node 4, and the number of nodes here is 5. Now, if this particular cluster gets split with nodes 1, 2, and 3 in one part and nodes 4 and 5 in another part, we can ensure it's a single split brain. Okay, there are 2 subclusters. We can ensure that in this particular case, the subcluster which contains nodes 4 and 5 will have full availability as well as full consistency guaranteed for all reads and writes for that partition. Okay, so things can continue, but then that partition is not available in nodes 1, 2, and 3. It doesn't have any copy anyway. So and the nodes know, each of the subclusters will know exactly what this is. That's kind of how our rules work, because they all know what the roster is, so they can make a determination. Now, if you look at the next picture, the split happens slightly differently. Let's say the nodes 1, 2, 3, and 4 form a cluster, which is up and running. And node 5 is its own cluster or just down. We don't know which. And we actually optimized for the rolling upgrade case. We don't want any service to ever be down because it's going through an upgrade. That's kind of a design principle from day one. Now, we also want to maintain strong consistency during that period. What you don't want is that some data is unavailable when you're doing a rolling upgrade. And therefore, your services are very spotty. Some user will be okay to, can transfer money, others can't. These are not things which businesses can deal with easily, right? It creates a bunch of customer service calls and very bad user experience. So from a platform point of view, our design point is a rolling upgrade has to happen with absolutely no downtime. Now, so what do we do? So in this particular case, right, the rule says that since this one is not available, this is part of a 4-node cluster out of 5. That's actually, I won't go into the details, it's called a supermajority cluster because it's got more nodes, right? Because you have 2 copies. So if 2 nodes are down in a 2-copy cluster, you have compromised some data. Okay, let's assume that the nodes go down quickly after each other, right? One node could go down and you could rebalance the whole cluster. That's not the case. One node goes down within like a minute, another one goes down. So then you have your compromise. In this particular case, one node has gone down. Now, these 4 are together as a cluster. We can actually maintain consistency by making the partition available in the 4-node cluster, but we have to create 2 writes because it's a 2-replica cluster. Every write has to create another one. Note that you don't wait until all of the data in the node 4 has been copied to node 3 before continuing. It's all right. It actually, we can prove that this will actually work. Now, this node, oops, what did I do? Okay, so this node actually is out, and then this has been going on for a while. Now, just imagine that this comes back and rejoins it, right? This is a rolling upgrade case. Then you will have some changes here. This particular node 4 has all the changes. All the writes after this node went down are captured in node 3. Now, if you just assume node 5 comes back and node 4 goes down, and you're doing a rolling upgrade, right? Between node 5, which had all the data before the first kind of split, and node 3, you have all the data. So you can actually continue. However, every read will now be a little slower because you have to check both, because you don't know that node 5 knows that it came back up, but it was not there for a while, and then you would have to go check 3 to see if there any changes have happened. Okay, so that'll be a little bit slower, but given the speed of Aerospike, everything else I talked about, it's still acceptable. Instead of a millisecond, it might be like a couple of milliseconds, and it might still be acceptable for you to continue. So a rolling upgrade in this particular situation will continue. There are cases, just to point out, where it is possible that you split into 3 ways this way, right? 1, 2, 3, 4, 5. There are 3 splits. Nothing, this partition is not available at all in that case. So we're trying to optimize for certain normal occurrences. Single split brain, we can continue. Also, basically, a rolling upgrade, we can continue. So those are the kinds of things we optimize for. And just a little bit on the writes. I already mentioned this. Every write has to go through every copy. Okay, that's basically what it's saying. That's important. And we can actually afford to do that because of our speed. Rack awareness is a piece that's really important also. What it allows us to do is to create higher availability scenarios based mapped to existing failure domains, right? Typically, in an AWS situation, you will put each rack in an availability zone, and then let's say you run your entire cluster in a region with 3 copies. You can use 3 availability zones if they're available. Not every region might have 3 availability zones, but if it is, you can run 3 copies, 3 racks, each one in its own availability zone. You could also run 3 copies, 3 racks, and 3 regions. Those are options available to you. I mean, there are trade-offs I'm going to talk about. Last slide on the transactions piece. It's just actually putting it all together. Okay, so what we can do is, here is a copy, here is actually a real configuration from a deployment where you have 3 racks, 3 copies. but these racks are in regions which are separated by large geographical distances. So what is the trade-off in this case, right? Trade-off is write latency will be much higher, 100 to 200 milliseconds. Because of the way every rack and copies are aligning, reads can still be sub-millisecond because you can read locally. You can configure the client's read locally. So you could, this is actually actual configuration used for money transfer operations. So people are talking today about, is 2 seconds enough for let's say you're transferring a few dollars to a friend. Is a couple of seconds enough? I think it's enough for the other person to get the money. A couple of minutes is not. So given this is 200 milliseconds for a single write, even if you write like 5 writes, you'll be done well within a second, right? So that's actually fundamentally a use case on which this is deployed at scale. And essentially what you can do is, the beauty of this is, you can take out an entire rack for an upgrade. There'll be full availability of the system in the other 2 racks, okay? You're going to have to read the paper to understand why, but basically, just take my word for it, and you can go verify it later. And then and there's no operator intervention when it goes down. It automatically continues with the rules I talked about. Then it comes back in, it'll join with no operator intervention in this particular configuration. There are other configurations where you might need operator intervention, so you can decide which one you want. Because if you spend more money, as a rule of thumb, you will have less operator intervention, less worries at night, and so on. If you want to conserve and run a little bit, I would say, compromise in a normal situation, when something goes wrong, you might have to wake up and do things. Okay, that's typically how these things work. In this particular case, I've designed it so it actually works no matter what. And none of it has any data loss, it automatically recovers, low latency for reads, and so on. So a little bit on the performance results. Just to give you an idea, okay, this is done with AWS a while ago, but it still holds. You can think about it, right? I mean, what are we running? We're running like a 20-node Aerospike cluster, okay, on i3 ENs. It'll be even better with some of the instances that Sebastian talked about. You can go to i4Gs, i4Is, they'll be even better performance than this. But this is itself pretty impressive. So we can run about 5 million reads by itself, or you can run 3 million reads per second, 754K writes per second. This is running basically a 1 petabyte unique data compressed to 1/4. So the actual single copy of data is 250 terabytes times 2, 500 terabytes of actual data. I mean, the data itself being stored here. And then essentially you're running it at this many, and it's 20 nodes of Amazon. Okay? The clients have to be a lot more, because to pump this many transactions in there, we need a lot more client nodes. Okay? This is typically how servers work. Typically you run a server of 10 to 15 nodes of Aerospike, and you have like hundreds of client nodes in production. And that's expected. And the important thing is the latency, right? The latency is for reads is 100% less than 1 millisecond, and 99% for writes are under 1 millisecond. This is the kind of mission-critical workloads that you can run on AWS with Aerospike. Okay, it's really important to understand that you can, on the cloud, get the kind of experience for these workloads that many of you might have seen in bare metal over the years. Okay, and this is actually a fairly new development over the last 5 years. Before that, I think we had a lot more people using bare metal, but recently, virtually everybody using the cloud, because this is what you can get. And this is about a year and a half old numbers. These numbers are even better if I rerun it on i4Is. So I'm going to switch gears now to talk a little bit about AIML and how Aerospike has been applied to it and where we fit. Okay. Now, before I get into the Aerospike part, a lot of the AIML environment essentially is about ingesting a lot of streaming data and getting data from everywhere, putting it in, okay? And this data is growing like crazy. And then you process and then it has to be everywhere in multi-cloud, it has to be on the edge. But then you also have to reduce the resource consumption, right? With the whole thing about how can you run you got to feed the beast, so to speak, right? You have all this data which you have to process in order to generate the models, in order to be able to answer the queries and so on. Okay, and just generating the model itself, I'll show you, takes an enormous amount of effort. These are not my numbers typically, right? All of this so fundamentally there is a dichotomy between generating all of this data and doing the work, and also trying to be efficient and reducing costs. Because and the efficiency part is really, really important. And that's kind of what you see, right? I mean, if you look at the costs themselves, they are significant. These are like, studies from, the MIT Technology Review, UPenn, and some other MIT report, and so on. But if you look at it, right, essentially computers are using a lot of energy, is what they're saying. It makes sense. But just training a model, okay, has a lot of, CO2 kind of impact compared to even driving a car, which is kind of amazing. And the cloud computing, apparently the carbon footprint is very. And it's not actually a surprise that Sebastian had a slide about AWS working on reducing the carbon footprint in their data centers. Okay, because it becomes very quickly not affordable. Forget about the impact to the environment. It's just not going to become cost effective. And then it's all related in some sense. So if you look at the database capabilities needed for AI/ML, there are portions of which I think Aerospike fits, and others I think we don't. But fundamentally, the thing is, there's a lot of global data which is streaming in from multiple sources. There are people in our customer base who are using 40 different sources every month, and hundreds of data sources feeding data in. The contextual data is really important to do things like fraud detection, for example, to actually analyze and come up with intelligent decisions in real time. You need enough real-time data for context. Otherwise, you're only able to answer queries about the past, but you can't answer queries which are essentially related to the present. And that's fundamentally an important problem, which I think we are focused on from an Aerospike point of view. Right? It doesn't matter where the activity is. And then you usually ingest it using some tools like Kafka and Pulsar. But then you use this data for real-time decisioning. This has been going on, for example, like PayPal, Barclays, and so on, who do fraud detection with Aerospike. They take all of this data and then they feed it in to generate a fraud score. The other one is, how do you generate new models? Okay, this is slightly different because Aerospike is typically used in this area, real-time decisioning. Okay, generating a model itself again requires a lot of data, and these are typically company transactional data. So you have general data which is coming from everywhere else, but then everybody has their own transactional data which they don't want to load into OpenAI or Google or whatever, right? Nobody's going to do that. So they want to find a way to augment it and generate a feature store potentially. This is typically what we see is the feature store is where all of this is stored. And Aerospike has been heavily used in feature store over the years. And then you use those to generate from your data, and you can learn continuously. And this is a different kind of access. Real-time decisioning accesses, let's say I am transferring some money using PayPal or doing a transaction on PayPal, then it's only about where I am, the fact that I'm in Singapore, the Wi-Fi address I'm using on my thing, or the mobile gateway through which it's coming in. All of that is factored in to generate a fraud score. On the other hand, if you want to figure out how to generate a better model, you're going to look at everybody's data and then go figure out, oh, I made all these decisions. How good were these decisions? If I change the model, can my decisions be better? Those are the kinds of discussions which require access to everyone's data, and that will actually create a better model, and then you can then apply that model in real time. Okay, so there are two aspects to it that's really important to understand, and Aerospike can definitely be used in about 3 out of 4 cases here. And then in terms of feature stores themselves, they describe various features for particular, it could be a consumer, it could be like, it could be ad tech, for example, where they figure out which segmentation you're part of. It could be like the fraud score I talked about. It could be a recommendation engine, what kind of movies do I watch? All of those things actually get stored in a feature store, right? And it's an online store, which means that as I am actually watching movies and so on, it's getting updated, right? Or if I'm clicking on ads, it's even faster. It gets updated all the time. And then maybe I bought something, so then they will stop showing me that, right? They'll show me something else. So these are the kinds of online read write that happens. The other one is you have an offline thing where you basically read a lot, you ingest data from everybody, but basically you are trying to integrate with a lot of data sources, and you're trying to analyze, right? So, and then there's of course a very simple one, which is like metadata, which you can look up. And this is something which basically Aerospike is good for. And you just look up things. Because those things don't change as often. Whereas the ones which change are the online stores. And even offline, you get a whole bunch of data coming in. You're ingesting, and you're just analyzing it to generate new models and so on. So we call it, one is the edge and one is the core, is another term we've been using. You know, the online is the edge and the offline is the core. You can also call it the cold store as opposed to the hot store, you know. But it feeds back and forth, okay? It's very important to understand that all of this actually happens in order to actually make a decision about any question somebody asks about, what recommendation should I give, myself. Somebody's, like Wayfair, for example, is a customer. They have to show recommendations to users based on what they have purchased, what their actual activities are. All of that has to actually happen in real time. Now here's an example of Quantcast. Again, look at the kind of scale, right? I just point out the scale of things here without going into the details, right? 10 billion records, 1 million reads per second, 200,000 updates per second. This is a classic online feature store, right? Things are coming in, you're asking questions at very, very heavy rates. It's an ad tech kind of use case. And the way you do is, you basically evaluate the model, look up the features, figure out what the answer is, and then essentially, the answer is sent out. And how do you know whether you're right or not? You know by the fact whether, the ad is clicked on, whether it's, basically how much engagement you get. So that's constantly being measured. And look up latency, right? Essentially is less than 2 milliseconds. And a write, you will see this story, right? I mean, everything I talked about in terms of the platform, it's about SLAs. How can I drive more writes through the system? How can I read faster from the system while maintaining the lower SLA? How can I keep uptime with strong consistency more than somewhere else? All of this kind of adds up that you can basically be better than other systems, okay? I'm not going to go into too much detail about other systems, but that's kind of what we expect to do. And here's another one. This is another e-commerce provider. This was a competition with Redis, apparently. But the point is, Redis is a real-time database, real-time system. I wouldn't call it a database yet. But the point is, it's as fast as anything you can write. It doesn't scale, okay? So that's kind of why we're better. It's because people have to build stuff on top of it, in many cases, in order to make it work, make it elastic and so on. And that's where the advantage for Aerospike comes in. The partitioning I talked about, that's what it gives you. We do better partitioning than what anybody can do by themselves. It's not like we doing it. It's RIPE-MD 160 doing it. The algorithm is that good. So we don't have to worry about somehow the actual domain of the data getting skewed in some way, that our partitioning algorithm will be skewed. It won't be. Okay? That's guaranteed by the RIPE-MD 160. And the fact that we also added a uniform partitioning balance algorithm on top of it. That's ours, right? So together, what you get is the ability to handle very high scale. And that's what it means when it says slowing the overall response time. It slows only when you scale. And that's what we don't do. Again, all of the work we've done in terms of our distribution, the speed out, the scale, reducing the cluster sizes, it all points to this exact one result that you see here, right? There's a whole bunch of details here I will skip, but I don't think it's relevant. This is just this is what Aerospike, the product is, okay? Just so you understand, I won't point to every detail, but these are data sources, these are data sinks, okay? But here's the thing. The database itself, right, supports multiple models. And that's fun. We support SQL through Presto, just so you know. We're not a native SQL database. Okay, but these three are native. Key value, document, graph are native to Aerospike. The platform that I talked about in terms of how we scale, how we essentially scale up, scale out, how we build these distribution, transactions and so on, we can apply it to multiple models. Okay, not relational though. Relational is its own body of work. I used to work in that area for a while, but that's a different kind of what I would call area, which we don't do. And then there's a whole bunch of other things I already talked about. We run everywhere, right? All the clouds and everything. But also, we can ingest data, right? We talked about ingestion for AI. We can ingest data into Aerospike through any of these connectors. Like it could be Kafka, it could be Pulsar, pick your own. You can write your own if you want. But the protocols are pretty straightforward. We can also, what I would call, move data from Aerospike to here. These are like what I would call as, these are streaming connectors. These are data access connectors. So data lives in Aerospike, but you can access it from Spark, from Elasticsearch, et cetera, et cetera. Okay? There's a whole bunch of stuff. There's 2 more slides. This one is in the graph database, right? This is our algorithm for graph. And the important thing is, we haven't built all of the APIs for graph ourselves. We have an expert team who basically built out Gremlin and Tinkerpop. They're the ones who invented it and built it in open source. We have taken the same programming model of Tinkerpop and Gremlin and applied it on top of Aerospike using what I would call as a compute layer on top of the data layer. Okay, and that's kind of how this works. And there's a whole bunch of details behind it. And the Aerospike database, of course, is here. All of this is the Aerospike graph service in front of Aerospike. And then you can then write your applications using the Gremlin as a query language and Tinkerpop as your programming model. This is already deployed, for example. And this runs against the same scalable platform that I talked about today. We are now working on the vector database. Graph and vector are 2 sides of the coin, in my opinion. Graph, the links are direct. Vector, you're inferring these links by actually computing on a domain the various vector values for the data that you're feeding in. And then you have to apply to that certain specific things, called RAG, is a scheme that you use, retrieval augmented generation. So essentially what it means is, otherwise you get a very approximate thing. How do you kind of fit it to the actual data that you have in the database? So we have ways of doing that. That's what we're working on right now. How do we make sure that we can integrate? First of all, we got to get the performance of a vector search really commensurate to the kind of differentiation that Aerospike brings to other searches. Okay, we're working on that. And then how do we then integrate it with other secondary indexes, which is not vector? So all of that is in process. This is already in some kind of preview alpha version. We are working to kind of implement every other feature, and release it this year. And the idea is trillions of vectors, trillions of edges. That's the kind of stuff for graph. We're about like large scale. So you're not going to use it for a small system. But when scale becomes big, which is actually kind of happening in many of these cases, like I talked about, right? So this is where I think it's going to really help. And that's the, if you want to reach out, contact us, feel free to. Any questions?
The floor is open. If you have any questions, I can pass the mic around.
Because you talked about all the, I don't know how many of my friends knows about the complex on, the compute engine and the storage engine and the modern way of accessing it. How long this technology exists, how deeply now penetrated into the market at this moment?
I think the technology has, we started it in 2009. So we've been doing this for about 15 years now. And if you look at some of the people who are using our product, also, I think many customers in Singapore, like DBS, for example, use us. I can pick a whole bunch of names, about 200 to 220, 250 customers worldwide. Many of the, as I said, a lot of it is about scale, performance, mission critical nature. So those are the customers we have. So you will recognize any name I say typically, in any market. Like, in India it's Airtel, in US it's PayPal, Nokia, Europe it's Barclays, Singapore is DBS, as I mentioned, and so on and so forth. Okay, so is it well penetrated? Not enough. That's kind of our goal is to increase awareness. That's one of the reasons we're here, and to figure and everywhere else actually. And that's kind of my main job these days is to figure out how to get more people to benefit. It doesn't have to be really a large company to benefit from this. Many of our customers, original customers, were startups who grew really fast. You need to be in a market where you need to grow fast, okay? And then Aerospike is a technology with which you can actually grow without having any hiccups for a long time, at least 12 years from our early customers. That's the idea. Yes, we run, and we have actually a partnership with AWS where we have collaborated with the AWS product teams for some of those instance names we were using, i4Is, i4Gs. So all of those, I think the Nitro SSD is a great, I talked about hybrid memory architecture. This was invented in 2009. Nitro SSD is a few years old, right? So what I mean is we've been working on this and the market has been coming to us in some sense. And that's been going on for a while. And we worked with, in the early days, Intel, Micron, and so on. And now with the cloud vendors, especially AWS.
Any more questions?
Thanks for amazing talk. We work in healthcare. So in healthcare, a lot of problems, especially on latency and throughput and storage even, is around the imaging side of things. So I wasn't clear if it was imaging was covered as well.
We are used by one of the largest healthcare providers in the US. This is Kaiser, prominent if you've heard of them. They have about tens of millions of customers. And they use us, they've started using us, so I wouldn't say they use us. Started using it for patient 360, they call it. It's not really for image processing. We're not actually a fit for just processing an image. But what we can do is do lookups, thumbnail lookups we're very good at. We are good at making sure that all the data which needs to be available at the fingertips of a physician is actually readily available, right? That is the kind of applications where you want to integrate all your systems into a database. So then, for example, like atrial fibrillation information and things like that, that's all stored in Aerospike. That's kind of where they're starting to do that. That's one kind of customer 360 for one kind of healthcare, okay? There's another one we have, which is more on the real-time thing. Monitoring, Abbott Labs, for example, uses, it actually came through NewU, I think is the name of the company, got acquired by Abbott, but they have launched a service for monitoring, I think it's sugar levels, right? Diabetes kind of thing. People wear these devices and they can real-time monitor. And frankly, I'm not boasting or anything, we can easily, with the kind of capacity we have, we can handle the 6 billion people in the world all having a device. We can handle that level of throughput and stuff. We can actually do it in real time, right? I mean, not we. I mean, our software with all the things I talked about, the Amazon instances, the SSDs, everything exists to do it. But medical stuff is very difficult because there's a lot of security and what I would call privacy things that will be taken care of. But we can, it's doable, is all I'm saying. The horsepower exists, and there's a lot of work has to be done to make it happen. But yeah, so we're used for those are two kinds of use cases we've been used for in healthcare.
Yeah, so what's your integration with Azure? That's my first question.
This is an AWS.
Yeah, and I'm just.
We work on Azure, yes.
Oh, okay. And I
all
don't-
the clouds.
Okay, but is your closest competitor Cosmos DB? Like, curious to understand, like.
Cosmos, that's actually an interesting question. DynamoDB, Cosmos DB, Bigtable. They all, for smaller workloads and different workloads, I would not even smaller. Cosmos can be used for large workloads. But if you don't have this kind of latency and throughput requirements, they all work. None of the databases which are there don't work or anything. They all work, okay? I'm a database person. But there are certain kinds of SLAs and application level requirements that businesses may have, that's where I think Aerospike shines, right? So if it is a real-time decisioning, then if you have scale, it's not just about scale, it's also the expense in terms of how much it costs, right? Those are things you should determine by yourself. You can compare DynamoDB with
Because that
cost.
was the next question, right? Like, do you have any kind of cost benchmarks? Because I'd be curious to.
We can, I think we can help you with that, but it would not be appropriate for me to sell those kinds of things. But the point is, I look at it from the capability point of view, okay? What we are doing is fairly unique. It will handle the kind of applications at scale, and that's where we can compete with any database out there. Not specifically Cosmos, but yeah, I mean, we've had people who have, who looked at all of these and picked us. Let's put it that way.
Yeah, what's your licensing model?
I think I'll defer to. We can chat about that, but
We can definitely keep that for the questions for the networking session that we have coming up.
Okay, I have a question. Since you mentioned like you have started working with startup as well. So with respect to startup, what is the minimum requirement so that aerospace will be the right fit for the
yeah.
startup? Like
Typically, not at the idea stage. Let's say the startup has reached the point where it has a product and it requires scale. Okay, and it varies, right? Typically, we look at the funding level of the startup sometimes. So you're basically going to be here to stay, in some sense, and you've gotten traction, right? That's kind of how. I'll just go back in time. So for the couple of people who used us, one was a company called AppNexus. Another one is a company called the Trade Desk. Both of them became eventually huge organization. Trade Desk even bigger. It's like a 50 billion valuation company right now. It's still independent. AppNexus got bought by many areas, but finally it's ended up at Microsoft. Okay, but they use Aerospike. They started using Aerospike when they were probably about 20, 30 people companies, where they knew the business was taking off. They basically had enormous growth ambitions, and they didn't want to like take a chance on some other technology just because it was native on the cloud or not. It's like if you know your business well, and then you'll be able to determine if the fit is good, right?
thank you.
Follow-up questions, I think, related to the two. So one is the cost. Can we recommend this to our customers whose budget is lower, like in Myanmar or in Africa region, right? And how effective it is for the data migration part? So let's say we are using SQL Server or Postgres and we want to migrate to.
Yeah, let me say something. So typically, people don't migrate to Aerospike from relational database applications which work well. The place where you should look for is if they are already struggling with a SQL Server or what is the other one, MySQL application, they're putting caches in front of it. And then they're finding that they put a Redis, and then they're struggling with that. What Aerospike can do is we can replace both the cache and the relational database with just Aerospike. Because our database is as fast as a cache. You don't need a cache in front of us. Right? We've even used as a cache in front of Cassandra sometimes, which is kind of crazy, but we've been used like that. But the thing is, if it's real time they are struggling with on a relational database, we fit for sure. But if it is just a relational database which they are working fine, I wouldn't. I would actually recommend if they are really looking for a distributed SQL without a performance kind of SLA or whatever, without not even using a cache now. There are products like CockroachDB, Yugabyte, which actually fit. They are distributed compared to these, right? If distribution is what you're going for, not really latency and scale, there are good relational database products today.
Okay, if there are no more questions, or if you'd like to think about more questions, let's leave it for later. Thank you so much, Srini, for that insightful session.